supermassive black holes. A supermassive black hole, SMBH or sometimes SBH, is the largest type of black hole, containing a mass of the order of hundreds of thousands billion times the mass of the Sun. This is a class of astronomical objects that has undergone gravitational collapse, leaving behind the spheroidal region of space from which nothing can escape, not even light. Observational evidence indicates that all or nearly all massive galaxies contain a supermassive black hole located at the galaxy's center. In the case of Milky Way, the supermassive black hole corresponds to the location of ADRESS A at the galactic core. Exploration of interstellar gas onto supermassive black holes in the process responsible for powering quasars and other types of galactic nuclei. The black holes have properties that distinguish them from lower mass classification. First, the average density of a SMB is defined as the mass of the black hole divided by the volume within Schwarzschild radius can be less than density of water in the case of some SMBSs. This is because of Schwarzschild radius is directly proportional to its mass. Since the volume of a spherical object such as the event horizon of a non-rotating black hole is directly proportional to the cube of the radius, the density of a black hole is inversely proportional to the square of the mass, and thus higher mass black holes have lower average density. In addition to tidal force, in the vicinity of event horizon are significantly bigger for supermassive black holes. The tidal force on a body at event horizon is likewise inversely proportional to the square of the mass. A person on the surface of the Earth and on the event horizon of a 10 million black hole experience about the same tidal force between their head and feet. Unlike with stellar black holes, one would not experience significant tidal force even every into the black. Some astronomers have begun labeling black holes of at least 10 billion as ultramassive black holes. Most of these, such as CON 680, are associated with exceptionally energetic quasars. The question is how a supermassive black hole is formed. The origin of supermassive black hole remains an open field of research. Astrophysicists agree that once a black hole is in place in the center C, it can grow duration of matter by merging with other black holes. There are, however, some hypotheses for the formation mechanics and initial masses of the progenitors or seeds of supermassive black holes. One hypothesis is that the seeds are black holes of tens or perhaps hundreds of solar masses that are left behind by the explosions of massive stars and grow by excretion of matter. Another model hypothesis that before the first star's large gas household could collapse into a quasi-star, which would in turn collapse into a black hole of around 20 solar masses. The quasi-star becomes unstable to radial perturbations because the elections positron bear protection in its core and could collapse directly to the black hole without a super explosion, which would eject most of its masses, preventing the black hole from as fast. Given sufficient mass nearby, the black hole could accelerate to become intermediate mass black and possibly a SMBH at the acceleration rate possessed. Another model involves a dense stellar cluster undergoing core collapse as the negative heat capacity of the system drives the velocity dispersion ballistic speed. Finally, bimodal black holes could have been produced directly from external pressure in the first moments after the Big Bang. These primordial black holes didn't have more time than any of the above models excrete, allowing them sufficient time to reach supermassive sizes. Formation of black holes from the deaths of the first stars has been extensively studied and corroborated by observations. Other models for black holes formation listed above are theoretical. The difficulty in forming a supermassive black resides for enough matter to be in the small enough volume. This matter needs to have very little angular momentum. In order for this to happen normally, the process of acceleration involves transporting a large initial endowment of angular momentum outwards, and this appears to be the limiting factor. This is a major component in the theory of acceleration death. Gas acceleration is the most efficient and also the most conspicuous way in which black holes grow. The majority of the mass growth of supermassive black holes is thought to occur through episodes of rapid gas acceleration, which are observable as active galactic nuclei or quasars. Observations reveal that quasars were much more frequent when the universe was younger, indicating that supermassive black holes form a major constraining factor for theories of supermassive hole formation. Supermassive black hole formation is the observation of distant luminous quasars, which indicate the supermassive black holes of billions of solar masses had already formed when the universe was less than 1 billion old. 1 billion years old. This suggests that supermassive black holes arose very early in the universe. Inside of a massive galaxy, a galaxy exists in the observed mass distribution of black holes. Black holes that from dying stars have masses 580 solar masses. The minimal supermassive black hole is approximately 100,000 solar masses. Mass scales between these ranges are dubbed intermediate mass black holes. Such a gap suggests a different formation process. However, some models suggest that ultraluminous X-ray sources ULX may be black holes from the missing group. There is, however, an upper limit to how large supermassive black holes can be. So-called ultramassive black holes UMBH, which are at least 10 times the size of supermassive black holes, appear to have a theoretical upper limit of around 50 billion solar masses. As anything above this slows growth down, the slowdown tends to start around 10 billion solar masses and causes the unstable acceleration disk surrounding the black hole to coalesce into stars that orbit it. A small minority of sources argue that distant supermassive black holes whose large size is hard to explain so soon after the Big Bang, such as ULAS J1342 plus 0928, may be evidence that our universe is the result of a big bounce instead of a big bang, which these supermassive black holes being formed before the big bounce. Astronomers are very confident that the Milky Way galaxy has a supermassive black hole at its center, 26,000 light years from the solar system in a region called Sagittarius A, because the star S2 follows an elliptical orbit with a period of 15.2 years and a pericenter closest distance of 17 light hours, 1.8 into 10 power 13 million 28 years from the center of the central object. From the motion of star S2, the object's mass can be estimated as 4.1 million solar masses, or about 8.2 into 10 power 36 kg. The radius of center object must be less than 17 light hours, because otherwise S2 would collide with it. Observations of the star S14 indicate that the radius is no more than 6.25 light hours, about the diameter of Uranus' orbit. No known as astronomical object other than a black hole can contain 4.1 million solar masses in this volume of space. Inferred objects of bright flare activity near Sagittarius A show orbital motion of plasma with a period of 45 plus minus 15 minutes at a separation to 10 times the gravity. Is consistent with a circularized orbit of a polarized hot spot on an accretion disk in astromagnetic. The radiating matter is orbiting at 30% of speed of light, just outside the innermost stable circular orb. On January 5, 2015, NASA reported observation an X-ray flare 400 times brighter than usual, a record breaker from Sagittarius A. The unusual event that have been caused by the breaking apart of an asteroid falling into the black hole or by entanglement of magnetic field lines within gas flowing into Sagittarius A, according to astronomers. The ambiguous dynamical evidence for supermassive black holes exists only in a handful of galaxies. These include the Milky Way, the local group galaxies M31 and M32, and a few galaxies beyond the local group, example NGC 4395. In these galaxies, the mean square or RMS velocities of the stars or gas rises proportionally to one or near the center, indicating a central point mass. In all other galaxies observed to date, the RMS velocities are flat or even falling toward the center, making it impossible to state with certainty that a supermassive black hole is present. Nevertheless, accepted that the center of the nearly every galaxy contains a supermassive black hole. The reason for this inception is the M-sigma relation, a tight low-scatter relation between the mass of the hole in the 10 or so galaxies with secure sections and the velocity dispersions of the stars in the bulges of those galaxies. This correlation, although based on just a handful of galaxies, suggests to many astronomers a strong connection between the formation of the black hole and the galaxy. Its nearby Andromeda galaxy 2.5 million light-years away contains a 1.1 to 2.3 into 10 power 8, 110 to 230 million solar masses. Central black hole significantly larger than the Milky Way's largest supermassive black hole in the Milky Way's vicinity appears to be that of M87 at a mass of 6.4 plus minus 0.5 into 10 power 9 solar masses, that is 6.4 billion solar masses at a distance of 53.5 million light years. The supergiant elliptical galaxy NGC 4889 at a distance of 336 million light years away in the Coma Berenices constellation contains a black hole measured to be 2.1 into 10 power 21 billion solar masses. Masses of black holes is quasars can be estimated via indirect method that are subject to substantial uncertainty. The quasar TUN 618 is an example of an object with an extremely large black hole estimated at 6.6 in 10 power 10, 66 billion solar masses. Its redshift is 2.219. Other examples of quasars with large estimated black hole masses are the hyperluminous quasar APM 08279 plus 5255 with an estimated mass of 2.3 and 10 power 10 23 billion solar masses, and the quasar S50014 plus 81 with a mass of 4.0 into 10 power 10 40 billion solar masses, or 10,000 times the mass of the black hole at the Milky galactic center. Some galaxies, such as galaxy 4C plus 3711, appear to have two supermassive black hole antecedents forming a binary system